All right, so here we are on lecture number 3. Let me remind you of some things coming up. I just did put some things on Moodle. I put the first homework assignment for week number 2. So now if you look under week 2 homework, September 5th to the 11th. We have Monday off, that's Labor Day. So the next assignment is due next Wednesday, 5 days from now, September 7th. And your typical kind of thing, studying some sections, doing some problems to prep you for the mini exam on Monday the 12th. This time for both Chapter 5 and Chapter 6 at the end. I did just put the solution key for Chapter 6 up as well. Actually, I better check that. I think I did. And then some more problems to work on that you'll actually turn in like today from section 7.1 and a little bit from section 7.2. We're going to introduce a topic called integration by parts during lecture B today. Do make sure your name and PO and homework number is in the top right corner. Some of you hadn't gone to your POs as of yesterday, or at least checked in with the post office. That is how your quizzes are going to be returned, as well as homework and exams. So make sure you make a habit of checking your PO, and make sure you know your PO number, post office box there. So that'll be due at the beginning of class, and again, you get help in Math Lab. Math Lab is closed for Labor Day, and I believe also on Sunday, the day before. But I think they open on Tuesday. I'll double check that and see if I can find out. Once again, we'll have a quiz in the middle of class. Today's quiz only includes substitution, and I do want you to show your substitution as well. Just letting you know, a little preview of that. Next Wednesday's quiz is going to involve 2 integrals. One of them is going to be a substitution, and one will be using integration by parts. Let me check. Did I put that other solution key up here? No, I did not. Okay, good that I checked. I still have to do that for Chapter 6. There's so much stuff with Moodle these days in all the classes. It's like, I can't remember, did I do that for this class or that class or neither? You know, it's hard to remember it all. I did put up the last lecture from Wednesday, Lecture 2A and Lecture 2B on Moodle. Those are links to YouTube in case you want to rewatch parts of those. Or for future students, you should be watching those as what you do. It's an online class. All right, so what are we doing today? I know that probability example was kind of a hard thing to wrap your mind around, so we're going to spend a little time reviewing that here at the beginning, exponential distribution. We're going to do some tricky substitution problems and review the fundamental theorem in calculus, and use that FTC in Lecture B to try to answer the question, why does substitution work? And then we will introduce integration by parts. What's the neat thing I want to show you today? Well, this is relevant for homework, actually. I'm going to show you some stuff about inflows and outflows. What do I mean by that? Imagine a tank that can have water enter and exit. And magically, this water is going to be both blue and red. Okay, I'm using different colors because the red is going to represent how full the tank is, and the blue that you see there is representing water, in this case, going out. I can also have water coming in. So I'm using the different colors to help you see how full is the tank and what's the flow rate. The initial time I'm on purpose taking to be not 0, but in fact -3 here. The initial water amount, if you will, is 4. I didn't put units on here. Could be liters, could be gallons, whatever. The initial rate of change of the volume with respect to time is negative because water's going out. Maybe I should say colored liquid. Okay, I'll say water. Red water and blue water. As time goes by, these graphs change and the situation in the tank changes. See what's going on here? Focus on the blue graph first, actually. Anytime that blue graph is negative, water is flowing out. Anytime it's positive, it's flowing in. The higher the blue graph is when it's positive, the faster the water is going in, represented by thicker thing there. And the lower it is negatively, the faster it's going out. And the red, again, is the water amount, the volume, or the level. One of these functions is the derivative of the other. And then in reverse, one of them is the integral of the other, and it, of course, reverses. Which one? Is the red the derivative of the blue, or is the blue the derivative of the red?
The blue is the derivative of the red.
That is correct. The blue is the derivative of the red. Okay, ignore the tank for the moment. Focus on that blue curve. Focus on, maybe I should stop the animation. Focus on the graph here, the blue graph. Actually, let's focus on the red graph, okay? The blue is the derivative of the red. So if you focus on the red graph, anywhere you want, the slope of the tangent line at that point should be given by the value of the blue graph. So for example, right about here, the slope of the tangent line is pretty high, pretty steep. And the value of the blue graph is high. In fact, at time 0, it looks like it's at a maximum. So the slope of the red graph is maximized there. On the flip side, right about here, perhaps at time 3 or so, the red graph is steepest going down, biggest negative slope, and the blue graph has the biggest negative value. The blue is the derivative of the red. It's the rate of change of the red. Where the red has a slope of 0 like there, the blue graph has a value of 0. Critical points for the red correspond to the zeros for the blue. Conversely, if the blue is the derivative of the red must be the integral of the blue. If I integrate the blue over any interval of time, it'll give me the change in the red over that same interval. So for example, and focus just on the graph, if I integrate from -3 to about, I don't know what, -2.25 or so, the integral of the blue is some negative number because the graph is below the axis, indicating that the change in the red is negative. The red goes down, the volume goes down. Integrate over this little piece, the integral is positive, so the change in the volume, the red graph, is positive, but not very much because that's not very much area. This looks like the opposite amount of area. Well, the same area, but counted as a negative for the integral, so the red graph's got to go back down by the same amount that it went up right there. Integrating the blue over any interval gives you the change in the red. That's the essence of the fundamental theorem of calculus. In fact, you're used to seeing it written in this form. At least the equation part of the theorem. An equation in and of itself is not a theorem. There are implicit assumptions that I had not bothered to write down. In this case, the main assumption is that the capital F is an antiderivative of the little f over the entire interval from A to B. In other words, little f is the derivative of capital F over the entire interval. Usually you use this to evaluate a definite integral here, but you could also use it to sort of think it the other way. This is the change in the value of capital F. And another way to think of this equation is it says to find the change in capital F, how much does the red graph go up or down? The red graph is capital F. Integrate its rate of change. Integrate its derivative over that interval. So you can interpret it that way. To find the change in the volume, the change in the red graph, integrate its rate of change, the blue graph. You think of it either way, and they're both useful, actually. So that's my little demo for the day, and it is related to the FTC, which we will talk about more. Let's review that exponential distribution. Again, there's a lot of words there. You can't possibly digest that, I think, within 1 minute or something. Okay, again, here's the situation you want to imagine. Imagination is important here to relate it to real life. We're imagining observing an intersection. Cars going through an intersection. We've got our stopwatch on our phone or whatever. The moment a car enters the intersection, we zero out the stopwatch, and we hit it again the next moment the next car enters the intersection. Okay? How long did it take for that next car to come? Maybe 2 seconds, maybe 4 seconds, maybe 7.346 seconds. Took that long, you write it down, it's happening too fast to write it down. Somehow your phone sends a signal to somewhere to store those values that you keep hitting, that you keep keeping track of how long it takes until the next car comes in. And every time you hit it, it not only keeps track of how long it took till the next car, it zeroes it out for the next one. Probability is a way of assessing the likelihood of some event. For example, what's the likelihood that it's going to take between 3 and 10 seconds for the next car to enter the intersection? This function is called a distribution, also called a density for this probability model. I'm pretending is an accurate thing to integrate to get you the right answer. Now, I didn't base this on any data, but it seems like a reasonable model to me for some intersection somewhere in the world. Okay? You know, some intersections are busier than others, and so cars won't take as long to come through busier intersections as they will through less busy ones. But I'm imagining this is maybe not a bad model for some intersection somewhere in the world. And without explaining why, again, I say you got to integrate this distribution function, this density function, both words are used, to find this probability, the likelihood in this case that it's going to take between 3 and 10 seconds. Let me do it by hand this time. We did it with Mathematica last time. Those doors aren't closed. It's so loud out there. Sorry for people on the video of all that background noise. I think it's unavoidable with the room that we've got here. So that's the symbol for the probability, the likelihood that it's going to take between 3 and 10 seconds for the next car to come through the intersection. Without explaining why, I'm just pretending. Doing the integral will give you the right answer. Okay? We'll get into why that might be a good thing to do later in the semester. So you just do the integral and you're just trusting that that's the right thing to do. Okay, in this particular model, to do this integral, you want to use a substitution. That's what I'm talking about this particular example now, so that we can use a substitution. You've got actually a couple choices. You could let w equal 0.1t, or, like I'm doing, negative 0.1t. It actually doesn't matter. You can do it either way. If I do w equals negative 0.1t, then dw is negative 0.1 dt. If I had done the other one without a negative sign, then dw would also not have a negative sign. The answer's got to be positive. Probabilities are positive. They can't be negative. The final answer will be positive, but I don't make a mistake. This is a definite integral. We are going to ultimately use the fundamental theorem of calculus, but first we're changing the variable. And again, do it the way that I told you to do it. I want you, when you do a definite integral with substitution, to go to the new variable and change the limits of integration. Don't do it another way that you may have been told in the past, which is find the antiderivative first and then plug in the original limits. I want you to change the limits of integration and don't go back to t with a definite integral. Why? Because it's good practice, for one thing. It'll prep you if you can take multivariable calculus. It's also going to emphasize the truth of something, a theorem that we're going to prove in lecture B, essentially. So, I do that substitution. That exponent there becomes the w. I get an e to the w. W, not negative w, because w is negative 0.1t. But dw is negative 0.1 dt. So if you combine the positive 0.1 and the dt, it's actually a negative dw. But we can bring that negative sign out in front if we like. Change the limits of integration. When t is 3, what's w? Use that equation. When t is 3, w is negative 0.3. When t is 10, use this equation again, w is negative 1. That's the integral to do. It's a little weird because look, the top number is smaller than the bottom one, less than, on the number line. Further away from 0 as a negative number. That's not typical. But you can use a property of integrals to switch those limits around in the more ordinary way. You actually don't have to, but you can. Though if you switch them around to put the smaller number, the more negative number in this case, on the bottom and the bigger number on top, that negative sign now goes away. This one right here. That's a property of integrals from chapter 5. You switch those limits of integration around. You gotta, if there was a negative sign there to begin with, you get rid of it. If there wasn't, then you make a negative sign. The sign changes. And this is now the integral you do. Antiderivative of e to the w is e to the w plus c. Don't need a c, right? With definite integrals because it would cancel anyway. Integrate from negative 1 to negative 0.3, so you are plugging those numbers in. You get e to the negative 0.3 minus e to the negative 1. That is one form of the answer. I'm sure we can write it in a bunch of different ways. How will Mathematica do it? Did we do it last time? I think we did do it. I'll type it in first as the original integral from 3 to 10. The original one was integrating 0.1 times e to the negative 0.1. Remember, with e in Mathematica, you need a capital E, not a lowercase. Actually, Mathematica is going to find a numerical approximation to this answer. It's not going to write it in terms of e because I put decimals in there, actually. 0.372939. Is that really the same? Let me go ahead and take this quantity and plug it in. E to the negative 0.3 minus e to the negative 1. Hopefully that's the same. Nope, it's not. Where's my mistake?
We didn't do e to the negative 0.3. It's not
You just did e times.
Oh, times, okay. Thank you. There we go. It is the same answer. And it is the same answer as the other integral. The integral I ultimately did. Negative 1 to negative 0.3 e to the w dw. Which are all the same. When you do a substitution to a new variable and you change the limits of integration appropriately, those integrals are equal. And by the way, it doesn't matter what letter you use. You could call it u substitution, as many people do, and I could have written it ultimately as the integral from negative 1 to negative 0.3 of e to the u du. It's the same answer. Doesn't matter what the variable name is. Sometimes variables for integrals are often called dummy variables, which is because it doesn't matter is the idea there, what you call the variable. But in a sense, all variables are dummy variables. It doesn't matter what you call them. So we have good reasons, perhaps, of choosing certain things. And again, you should know that this simulation here, which I could ask you a conceptual question on exam 1, like a month from now, a month and a half from now, something like that, related to this. Do you understand the concept? What the simulation is doing, let's go out to 100, is it's simulating traffic, not literal cars going through the intersection that you can see, but the data that you've gathered. It's simulating what happened as you gathered data. Each dot represents a data point. And the idea of probability, the fact that this area was about 0.37, means about 37% of the data are going to be in that window. They're most dense where the graph is highest. That's why it's sometimes called a density. That's where the points, the data, are most dense. How many data are in there out of 100? 38 for this example, close to 37%. If I run it again, I'll probably get a different answer because that's the nature of randomness. Run it again. This is probably going to be a different number, 30. Not quite as close to 37, but not super far away. You should expect, since the probability is 0.37, to get relatively close to 37 out of 100 data points. That's the basic idea. You're simulating data. Which is a good thing. Like, what if the integral was really hard to do? You maybe you'd have to do the simulation to try to get the answer, perhaps. Actually, no, you can do numerical integration, but simulation is an important thing. All right, next let's do some tricky substitution problems. We'll try to do these fairly quickly. They are tricky. Remember that I said it's often, though not always, a good idea to let the new variable be the thing inside the cosine, or the thing inside the sine, or the thing that's in the exponent of the e. It's typically a good thing, not always. It doesn't always work. Substitution doesn't always help. It's not always helpful. It's always true. You can always do it, but it's not always helpful. In this case, the thing under the square root, the 3x plus 4, is the thing to try. It's not clear that it's going to help, though. This is less clear because, look, that's an x there. It's not a number. If that were the number 3, definitely letting w equal 3x plus 4 would be helpful because then dw would be 3dx. But it's an x there. So it's definitely not clear that it's going to work, that it's going to be helpful for doing this integral. But it turns out that it will be helpful. You just have to do a little extra algebra. Let w equal 3x plus 4. So this will get replaced with a w. dw is 3dx. That would also allow you to say dx is 1/3 dw. But what's the issue? What's the difficulty here still?
Can't get rid of that x.
Yeah, what do you do with that x? Solve it for x, yeah, you got it. Solve this equation for x in terms of w, that's the thing to do. It's not clear that it'll be helpful, but it's the only thing we can try. Let's see what happens. First subtract 4 from both sides, then divide both sides by 3. I hope you can do that in one step to see x is w minus 4 over 3. Or 1/3 w minus 4/3. We can replace x with that and see if it's helpful. All right, so let's do it. Well, let's go ahead and write it as 1/3 w minus 4/3. That's what x is, times the square root of w, which I think I'll write as w to the 1/2. And then dx is 1/3 dw. Looks worse, perhaps, doesn't it? It's actually better. Why is it better? 1/3 should be brought up in front. In fact, you can factor 1/3 out of that as well and have a 1/9 in front. Maybe I'll do that. What can I do with this w to the 1/2? Here's a hint. Watch my hand.
Distribute?
Distribute it through, yeah. You can't really distribute through here. I mean, you could treat the x as square root of x squared, at least when x is positive, and perhaps bring it under the square root, but that doesn't necessarily seem helpful. Yeah, distribute it through. I factored out that 1/3, I factored out that 1/3, and this 4/3 with a 1/3 factored out becomes a 4, or a minus 4. W times w to the 1/2 is w to the 3/2. Don't forget the 4 and a w to the 1/2. And that's doable. Maybe factoring up a 1/9 wasn't such a great idea, but oh well, we did it. Be careful, it's easy to make a mistake here. See what I did there? Add 1 to that exponent, 3/2 plus 1 is 5/2, divide by that same number. Add 1 to that exponent, 1/2 plus 1 is 3/2, divide by the same number. Careful with your fractions. Dividing by 5/2 is the same as multiplying by its reciprocal, 2/5 in front. 2/5 times 9 is going to be 2/45. W to the 5/2. I'm going to go ahead and replace W with 3x plus 4. 2/45, 3x plus 4 to the 5/2, and then minus 4/9 times 2/3 is 8/27. 8/27, 3x plus 4 to the 3/2 plus c. You'd never guess that would be the answer, would you? I'm pretty sure I didn't make any mistakes. I'd want to check it. If I did check it, I'd have to use the chain rule, or I could try to use Mathematica. It's possible Mathematica won't write it in this form. And I know Mathematica doesn't include the c. It's possible Mathematica might factor out a common factor of 3x plus 4 to the 3/2 out of the difference here. That could happen. I'm not going to take the time to see. What about this one? Getting close to quiz time. What should I do? Should I let W equal this thing on the bottom? If I do, it doesn't seem like dW is there sitting there for me. Is that helpful? Well, it's hard to say, but give it a try and see what happens. If W is 5 plus 8 square root of x, dW is going to be, well, square root of x is x to the 1/2, bring the 1/2 in front. 8 times 1/2 is 4. X to the negative 1/2. Don't forget the dx. Pretty tricky, but we can solve it, it turns out. You can solve this equation for square root of x in terms of w, and you can replace the square root of x down there with the expression you solved for here. So we're not solving this equation for x, we're solving it for square root of x, and then substituting there. Subtract 5, divide by 8. That is the square root of x. Now take that and plug it in there. Pretty tricky. 4 over w minus 5 over 8 dx, which is the same, careful with your fractions here, as 32 over w minus 5 dx. That 8 goes in the numerator with the 4. And then that's equal to dw. I want to essentially solve that for dx. That means dx is w minus 5 over 32 dw. And that can be plugged in there in terms of in place of the dx. It's a definite integral here, so we need to change the limits of integration. Use this equation right there. When x is 0, square root of 0 is 0, w is 5. When x is 10, actually I meant to use 9 there. I was doing it by 9 with a 9 by hand. And then for some reason I typed 10. Okay, that's supposed to be a 9. Make the square root nice. Square root of 9 is 3. 3 times 8 is 24, plus 5 is 29. You'd never guess that these two integrals are the same, right? Without doing this work. You'd never guess that this integral with a 9 there is the same as that integral with a 5 and 29.
Wait, so remind me again why you changed it from a 10 to a 9?
Because the square root of 9 is a nice number, 3. And the square root of 10 is not so nice. I wanted to type a 9, but for some reason I typed a 10. I was doing it by hand before class, and then I typed a 10. Is this integral easy to do? Yeah, it's not too bad, actually. You can think of this as like that as w over 32 minus 5 over 32, and you can divide everything by w. This becomes the integral from 5 to 29 of 1/32 minus 5 over 32w. Sorry, it's kind of a mess here. Hopefully the different colors help. This is not an ideal Roman. We have this posted in between. That's doable. One 1/32 w is the antiderivative of 1/32, and what's the antiderivative of 5 over 32w? You can bring the 5 over 32 out in front, so to speak. What's the integral of 1 over w?
Natural log.
Natural log of the absolute value of w, though w is going to be positive, so I really don't need the absolute value sign. I'll leave them there anyway. So we're going to get 29/32 minus 5/32 natural log of 29. Put all that in parentheses and then subtract 5/32 minus 5/32 natural log of 5. Can that be simplified? Yes, it can. Combine those two things, 29/32 minus 5/32 is 24/32, which is also divide everything by 4, or 8, and get 3/4. That's the same as 3/4. And then the logs can be combined as well using properties of logs. What would it be here? Those two minuses give a plus. The 5/32 can be brought into power. We have a minus there.
Wait, what?
I know I'm going fast. Just let me write down the answer. Natural log of 5/29 to the 5/32 power. Yikes. I believe, if I didn't make a mistake. Not such a nice number, but I think it's right. Better check. It's time for the quiz. I better check my work during the quiz, and we'll see if it was right after the quiz is over. Okay? Take the quiz.